Okay, let's start today's class. The class is on uh, a very brief discussion on randomized algorithms. Okay, so just in the last class we talked about a probabilistic method, and we learned that probabilistic. One example of maximum cut problem, and we had a theorem that the size of the cart for any graph g equal to v comma e, we can have a cart of size greater than equal to m by 2, where m is the number of edges present in the graph. Okay, and while proving that theorem, we followed three steps, basically two steps. The step one is forming an appropriate probabilistic space. Okay, for a suitable random variable, and in the next step, in the second step, we had computed the expectation of that random variable. Okay, so in a similar fashion, we will take up another example to illustrate randomized algorithm. And okay, so start what is so we shall have a motivation, that is a formal. I mean, in our case, that is the introduction. Okay. Take an example. Let's take an example. Algorithm. Okay. Okay. So let's take an example of quicksort algorithm. So in this algorithm, find, okay, remember the quicksort algorithm. We can have a look on this. Okay, so this is the picture. Okay, where what we are doing, suppose we are given a set like this, 11, 2, 9, 13, 57. Okay, so we take up an element, let's say this element to be a pivot element, and then we are finding a suitable position, the exact appropriate position of 11 in the array. Okay, so once we are finding the appropriate position, in this case here means the position where the crossover occurs. So here crossover occurs between means I and j crosses each other, and here we shall stop our iteration. So at this moment you are swapping the pivot element with that element where the crossover occurs. Okay, so the position j equal to 4 is the actual position of 11 in the sorted array. Then we split the array into two subarrays. So j equal to 4 is the position which is doing the splitting of the overall array into two subarrays. So this is one subarray and this is the second subarray. Okay. So this is the technique, right? So that's why we require to find a splitter. Okay. We are given a set of elements, let's say S. Okay, we require to find a splitter, let's say Y. Okay, Okay. Partition into, let's say, S1 and S2 such that uh, all elements in S1 are less than Y, all in S2 are okay. Then we do apply the same in S1 and S2 and so on and so on. Finally, we get what it is. Right? Now the question is, the question here, how to find such y. Okay, so in quick sort can be found of in y. Another way of finding y, that is that is uh, is randomly. Okay, so element is selected as y with some as probability is positive, we are sure that we shall get a correct answer, positive probability. Assumption this probability is fair. So this led us to motivate enough to go for randomized algorithms. Okay, so um, randomized algorithm method is known as the algorithm is known as, let's say, and QS. Okay, so is, you know uh, S and output is, sorry, yes. Algorithm is y uniformly at random, or we write this as u dot a dot r. Uniformly random means, let's say, okay, I will talk about it later. Then, okay, all elements are double. Okay, so right. Then all elements, y is the splitter, right? Select y uniformly at random from S, where all elements in S are equivalent to be selected. So or and okay, A's are compared with y to form S1, where all elements in S1 are less than y, and to form all elements in y. Okay. Next, we actually apply one and step two. Finally, okay, display S1, sorted S1. Okay, so this is our algorithm. Give some space. Okay, and what do we mean by uniformly at random? Means so it's a uniform distribution. Let's say if S is the probability distribution function CDF of S, of the elements of S. Okay. 1. This is, so this is the meaning, or this could, okay, for example, this is so, and what I want to take, I want to take any sample from here uniformly at, so this is the meaning of uniform distribution. The, okay, probability distribution function is looking like this. So from this distribution we are taking a random sample. So this is a uniform distribution and we are taking a random sample like this. Okay, that's why it is called uniformly at random. Okay, fine. So next we move on to, so in this regard we have a theorem. Theorem is that uh, expected, okay, so before that we can show that the time complexity of and QS order of n, okay, and to prove this, okay, to come up to this result we have a theorem that expected number of comparisons, randomized quicksort algorithm, most is at most okay, so where where Hn Okay, so we will prove this theorem so as to come up to the result. Time complexity of band q is equal to order of n log. Okay, okay, so let's go for it, proving the theorem. And while proving the theorem, we will see that we will use the probabilistic method concept little bit. Okay, so let let the highest number is is called an element of rank I. Noted as suffix and all. Then we assume find a random variable uh, corresponding to, okay, corresponding to comparison, okay, number of comparison between elements in S as follows. So this is xij. So this is my step one. Okay. If you want to think in a probabilistic method way, so we are in a step one. Okay, let me write that here. So this is probabilistic space. So xij equal to 1 if uh, S I J are compared. So Si means an element with rank I, Sj means it's an element with rank J. So these are compared in an example. Okay. Otherwise it is 0. Fine. So if one such comparison is done, then value of xij will be equal to 1. Okay, so that means uh, if I sum up all the values of xi, all the possible values of xij for all the possible values of j and I, then that summation will give us the total count of comparisons, right? So total number of comparisons will be, let's say that variable is x, and that is summation over two variables indexes are I and j, so it will be a double summation. So this is xij. First is I equal to 1 to n. One is based on j. So we will do comparison for when j is greater than I. Okay. Now step 2, computing expectation. So we are interested to compute the expectation of x. Okay. So what we shall have, equal to expectation of this double summation, and double summation will come out of expectation, so that we can write expectation of double summation. Okay. So in the next step we have xij. So okay, so at this moment we can't do anything because we don't know the value of xij. Okay, and we know that, oh, acha, expectation of this. Okay, summation over xij. I So at this moment of xij, right? So and we will see that expectation of xij is nothing but the probability that Si and Sj are being compared. So now we have to compute that what is the probability that Si and Sj will be compared in an execution. Okay, so our interest now moves towards finding probability uh, that two elements Si and Sj are being compared. Yet the probability that probability that Si and Sj are compared is Pij. So okay, so you can write that in probability that S Ij Sj execution okay. And to find out the Pij, we consider a quick sort problem tree construction problem. Capital T. Okay. All elements in S1 compared to Y to form F subtree of Y. Uh, all elements in will be will be right subtree, right? Okay, so all elements in a left subtree are less than Y and right subtree greater than Y. Okay, so stay here. There is no comparison when the two elements okay so is are belong to the two subtrees and there is no comparison I okay because all the elements of S1 will be compared to Y. No element in S1 will be compared to no element in S2. That means if Si and Sj are in different subtrees, okay, then there is no comparison between them. Okay, so in other words, we can say that if there is in and A, then one of them will be an ancestor node of so okay. So now in this regard we shall have two important observations. one observation is uh, okay. So before that, to understand that is uh, interested level order traversal of T. Traversal okay is a permutation while going from root node towards leaves okay increasing order of levels moving from left to right. This permutation B okay. So next our observation will be uh, SK is occurred earliest in pi compared to other elements such that so you consider all the elements which are having ranks between these two ranks I and j. So out of all these intermediate ranked elements, assume xk is one such element which has already occurred, which is occurred earliest in pi. This is the first element which has been which is occurring in the permutation. Now what we are doing, how to find such a permutation pi, which is the level order traversal. Okay, so in the permutation we assume that the first element which will be occurring, that is sk, and sk is having the rank between I and j. Assume this. Okay, so sk is this. Okay, okay. So then we can have this if belongs to ij. I mean Okay, does not belongs to ij. Okay, k does not belongs to ij means sk is not si or sk is not sj. ঠিক আছে? Then what will happen? K is some intermediate value between I and J. So that means uh, all the elements which are having rank less than K should be the elements belong to the left subtree of SK, right? So then, and one of them will be SI. So then SI belongs to left subtree of SK. Okay, SK. And as J is greater than I, and K is an intermediate rank between I and J. So all the elements which are having rank greater than K must belong to the right subtree of Sk, and one of those elements must be Sj. So Sj to right subtree of Sk. So in that case, then there is no comparison I and Sj, because they belong to different subtrees, and we have already come up to a fact that if these elements are belonging to different subtrees, they can't be compared, because a comparison is being done between an element of a subtree with the root node. One of them should be ancestor to the other. Okay, so they are not ancestor of the other. So here, that's why no comparison is being done between no comparison is possible between Si and Sj. So this is one thing. Next we have what happens if K belong to Ij. That means Sk is either Si or Sj. Okay, so then what will happen? So clearly Sj star of hence then there will be comparison between Si and Sj. Okay. So that means there will be a comparison between Si and Sj if one of them is ancestor to the other, and we have assumed that Sk is an element occurred earliest in pi. So combining this statement and the last statement, we come up to an observation. So here, okay, is a comparison between Si and Sj, One of them must occur here in pi. Okay. So next our second observation. Uh, then one of them must occur earlier in pi then then uh, then any other element SL such that I less than L less than H. Okay, this is the complete observation. Next we have observation 2, that is, so from the observation 1 we have come up to the conclusion that an element will be occurring in pi earlierly if that element is not in belong to this range in between I and j. So the element must be Si or Sj. So one of them, either Si or Sj, will be occurring earliest in pi as compared to all other elements Sl, such that L is between Ij. So only the terminal ranked elements will be occurring earlier in pi, the permutation pi. That's the point, right? So using that observation, we come up to, we want to make another observation, that is elements in the range I is equal to j minus, right? So okay, so j minus I plus 1, right? So I mean here either Si will be occurring earlierly in pi or Sj will be occurring earlierly in pi. So the number of ways in which Si or Sj that will be occurring earlierly in pi is 2. In 2 ways, right? That means those are the ways in which we may have a comparison between Si and Sj. So if there will be a comparison between Si and Sj if Si occurs earlier in pi or Sj occurs earlier in pi. So in two ways we can have a comparison between Si and Sj, and that has been understood in the with the concept of permutation pi, right? Fine. Now the total number of ways, so from OBVS 1 8 that number of ways in which comparisons are done between, yes, we are about to finish, so between Si and Sj, number of ways in which comparison done between Si and Sj is 2, full stop. So and the total number, no, we now come to the probability. The probability that probability Pij, and Pij is the probability that Si and Sj being compared. So in how many ways Si and Sj are compared? That is 2. So now we have to find out the total number of ways. We will divide the 2 divided by the total number of ways to get the probability Pij. So that's why we are interested to find the total number of elements in the range ij, that is j minus 1 plus I. And each range are probable, equally like. Okay, so we have the probability as j j minus I. So we have modeled this probability from this observation, the two observation. Okay. Now from equation 1, what we have, expectation of x equal to double summation expectation of xij. So from, recall that from 1 we get of x a double summation of expectation of xij, and that is your pij. So I am not writing that again, directly I am writing pij. This is I equal to 1, next j greater than I. J greater than I means j equal to I2 uh, n. Okay, so in the next line we can write equal to double summation Pij is 2 by minus I plus 1 n I. So in the next line we have double summation. Let's say this is k. We assume here k equal to j minus 1 plus, so this is something n. What we have, okay, so let me write here. So when j equal to I, it is 1, this is n. Okay, so 2 comes out of the summation. So okay, directly writing, okay, equal to 2 double summation 1 upon k, and in the next line write that it is less than or equal to. So in the second summation we have 1 to n minus I plus 1 number of terms. So here n minus in bracket I minus 1. So that is always less than or equal to the sum of terms consisting of n terms, right? So hence we can write here that is twice double summation 1 upon k, and here k equal to 1 to n equal to 1 2. Okay. So in the next line we can write that this double summation expression, this summation expression, this is actually hn, the very standard form, that is. So 2, we can prove this. It is provable. This expression is very provable. So no problem. Uh, you can see some reference. Okay. So where Hn is harmonic number as Hn summation over uh, upon k. Okay. So we got the result that expectation of x. So hence we have this. We have expectation of so this is and we also have a very important result. We also have a standard result, also a provable result. These are not required to prove here. So if we have some time later on, we can go for it. It's purely a mathematical tool we are using here. So we also have a very standard result, that is okay. Hn is almost equal to log n plus and hence that is almost equal to okay. So thus in the next line we can write that expectation of x are equal to log n. Okay. In the final conclusion, our conclusion is thus proof that the number of comparisons in the rand QS algorithm is actually giving us the time complexity. So the number of the time is greater than or equal to log n plus Tn So this is your C value, C n log n. So order of n log we have just put here. Okay. So just have a look what we have done. Okay, so our theorem was the expected number of comparisons in rank QS is at most twice n Hn. So expected number of that is Ex. So Ex was proved to be uh, 2n Hn. Okay, this is Ex is less than or equal to 2n Hn. That is the maximum number of the expected the maximum value of expected number of comparisons is 2n log n. That is proved, and from that theorem we come up to uh, the, the result that time complexity of rank-based algorithm is order of n. Okay, so this is one example. So how we can develop a randomized algorithm and hence its time complexity analysis. Okay, so I hope you have understood well. If you have any question, you can ask me, or we can stop here. I hope no question. We can stop here.